Hello everyone and welcome to my channel Computer Classes by Rachna. Now we are going to discuss AVL trees. If you have not seen my previous video about the binary trees, please see that first and then visit here again. AVL tree is also a binary search tree. So a binary search tree, as you already know, is a tree which has the values lesser than the node on its left side and value greater than the node on its right side. So AVL tree is also a binary search tree where every node has a balance factor of either 0, 1 or -1. Now what is a balance factor? The balance factor is the height of the left subtree minus the height of the right subtree. If you see 20, the balance factor of 20 is 1 minus 2 because height of the left subtree of 20 is the branch which is from 20 to 10, which is 1. And height of right subtree of 20 is the branches which are from 20 till the last node. So you can see the height of right subtree of 20 is 2, 20 to 30 and 30 to 25, or we can also consider 20 to 30 and then 30 to 35. So the height is 2 for the right subtree of 20. So 1 minus 2 equal to -1. The balance factor of 10 is 0 minus 0, 1 because 10 does not have left and right subtree. So 0 minus 0 is 0. Please note that the height of all the leaf nodes is 0. And the height of left subtree minus left subtree is also 0, which means balance factor of all the leaf nodes is 0. Leaf node is a node which does not have any left or right child. Then the height of 30 left side is 1 and the right side height is also 1. So balance factor of 30 is 1 minus 1, 0. So it is a balanced AVL tree. Now the thing is, how to make AVL tree balanced if it gets unbalanced after adding a node. Step 1. Check the balance factor of every node and let alpha be the node which is unbalanced from the bottom of the tree when we add a new node. Now step 2. If the balance factor of every node is either 0, 1 or -1, then there is no change. No rotation is to be applied. Step 3. Find the appropriate case of rotation out of the following. So we find out which rotation to be applied. There are 4 types of rotation and we have to apply the rotation to make the tree balanced. So let's find out the different types of rotations. There are 2 single rotations and 2 double rotations. The first single rotation is LL. The second single rotation is RR. Then there are 2 double rotations. The third type of rotation is a double rotation, which is LR. The fourth type of rotation is a double rotation, which is RL. Now let's understand with the definition what does they mean, and then we will see the examples. LL rotation. LL means when we add a node to the left child's left subtree of alpha. So when a balance factor of alpha is changed by adding a node into left subtree of the left child of alpha. RR rotation, which means the balance factor of alpha is changed when we add a node into the right subtree of the right child of alpha, which means alpha is a node, we have its right child, and right child's right subtree is the place where we add a new node, and alpha gets changed as a balance factor. Now, the third type is LR. LR means we added a node at the left child's right subtree of alpha. So when the balance factor of alpha is changed by adding right subtree of the left child of alpha. Then we have another rotation which is RL rotation, which is occurring when a node is added to the right child of alpha and in the left subtree of the right child. So the node at the left subtree of the right child of alpha is added, then we apply RL rotation. Now all of these above rotations can be explained by taking the same tree which was having values 20, 10, 30, 25 and 35. Let's say we want to add 5. So before adding, let's check the balance factor. The balance factor of 20 is -1. The balance factor of 10 is 0, 30 is 1, 25 0, 35 0. Now, after finding the balance factor, all the nodes are either 0, 1 or -1, so it is balanced. Now we add 5 to the tree. First thing, since it is a binary search tree, where will be 5 added? Let's see, 5 is less than 20. It should go to the left child of 20. Now we have 10. 5 is lesser than 10. So it should go to the left of 10. So 5 is added here. The balance factor of 5 is 0. The balance factor of 10 is 1. The balance factor of 20 is 2 minus 2, which is 0. The balance factor of 30 is 0, which is 1 minus 1. And the balance factor of 25 and 35 are also 0 because they are the leaf nodes. Since we have the balance factor as 0, 1 or -1 for every node, so no change. Next, we add 40. Now when we add 40, where will 40 be added? To the right of 20, to the right of 30, to the right of 35. So 40 is added here. Let's check the balance factors. 35 ka left child, the left child of 35 is not there, so 0 minus 1 minus 1. The left child of 40 is not there, right child of 40 is not there, balance factor is 0. The balance factor of 25 is also 0. The balance factor of 5 is also 0 because left child minus right child height is 0 minus 0. Now the left child of 10 is 5. So the height is 1 minus 0. The balance factor is 1. Now 20, the left child of 20, the left subtree of 20 is having the height 2. The right subtree of 20 will have the height which is for the longest branches. So we have 1, 2 and 3. Right child's, the right subtree of 20 will have the height as 3, not 2. We consider the longest branch. Alright. So it is 2 minus 3 which is -1. Since all the nodes have 0, 1 or -1 as the balance factor, so the tree is balanced. Now we add 45. Now look at the example here. After the 45 is added, we check the balance factor of all the nodes. 45 is added. The balance factor of 45 is 0. The balance factor of 40 is 0 minus 1, which is -1. The balance factor of 35 is 0 minus 2, which is -2. The balance factor of 25 is 0 minus 0. The balance factor of 5 is 0 minus 0, which is 0. The balance factor of 10 is -1. The balance factor of 20 becomes 2 minus 1, 2, 3 and 4. Height of longest branch is 4. So 2 minus 4 minus 2. The balance factor of 30 is 1 minus 3 minus 2. Now there are so many nodes which are not balanced. So we have 20 which is having balance factor of -2. We have 30 which is having balance factor of -2. We have 35 which is having balance factor of -2. But the thing is that we have to find out which node got imbalanced while coming from bottom to up. So the first node that got imbalanced was 35. So 35 is considered as the node alpha. Not 30, not 20. 35 is the first node which got imbalanced from bottom to up. So this is considered as alpha. Now if this is alpha, we have added 45. So it is added to the right child's right subtree. The right child of alpha is 40 and the 45 is added to the right side of right child. So right subtree of right child of alpha. That's why it is a case of RR rotation. This is a case of RR rotation. Now, what do we do when we have RR rotation? Let's read back. If we have RR rotation, we have to rotate alpha to the left. Look at case 2. If we have RR rotation, we have to rotate alpha to the left. Whereas if we have LL rotation, we have to rotate alpha to the right. So we will rotate alpha to the left. Now let's come back here. This is alpha. Now when alpha is rotated to the left, so what is going to happen? When 35 will be rotated to the left, the 40 will come up and 35 will move to the left of 40. 35 is rotated to the left, so 40 will come up and 35 will go down to the left of 40. So this is how we get rotating alpha to the left. 35 rotated to the left, 40 comes up. The right side of 40 was 45 and left becomes 35. Now we check the balance factor, and as you see, the balance factor of all the nodes is either 0, 1 or -1. So it is balanced now. This is the example of RR rotation. Alright, this is an example of RR rotation.